Start whenever you're ready.
Okay, so I can start, right? Okay.
Yep, go for it.
First, let me thank Flo and Joy and Thomas for the invitation to give this talk. Thank you very much, and thank all the audiences. So today I will talk about recent work joined with Toyomoki Arakawa and Anne Morrow. So about the associated varieties of alpha VOA. So okay, that's the outline of my talk. So the first I will to introduce about what is a Python algebra. And secondly, we will talk about the graded what is the Python algebra of alpha VAs. And the third part is the varieties of alpha VAs, and the last part is the varieties of alpha W VAs. Okay, so now we briefly talk about the vertex Python algebra. So because we have to use this to in our proof of a result of the first part, we use the Python vertex algebra. So recall that a vertex algebra V is said to be commutative if En is zero in this subspace in this. So for all A and in V and N is a non-negative integer. So a commutative vertex algebra is the same as the differential algebra, I think, in this year by Bouchard. So with this A dot B equals to is defined as A minus 1B. And the differential operator is just the translation operator of V. Now let V be a commutative vertex algebra. V is called the vertex Python algebra or Python vertex algebra. I don't know which one is the correct. So okay, if it is also equipped with a linear operation, just this way. So I'm sorry. I need to get forget to get the reference. I think maybe in the first. Oh, I'm sorry. Just Python, but I think for the first give the figure offering code maybe. I needed to make sure that okay. So I'm sorry. So with this linear operation, so we in this if we expand it in this way. So the this operator satisfies this and satisfies the following formulas. So with this relation. Now, vertex Python algebra V is called graded if there is a semi-simple operator H on V. So if it is a VOA, so this H is just the L0. So satisfy this relation. Okay. Now, an idea of V is a submodule I of V. Here I didn't give the definition of module. I think I don't need to give this, so you can imagine. Okay, when we know the definition of algebra, so it satisfies the DI this in this. So it follows that the quotient is also a vertex Python algebra induced by the original one. So now let R be a Python algebra. So in the X is the scheme of R, and the X infinity is the infinite jet scheme of X, and R infinity is this. Then we have the following proposition given by Arakawa. So there is a unique vertex Python algebra structure on this and satisfy the following relation. So now we also in the following we will need the Lie filtrations and the So now I introduce the filtration and the graded vertex Poisson algebra of alpha VOAs. First, I give so we introduce the one of the filtrations. So yeah. Now let V be a vertex algebra, and for any p non-negative integer p, define this subspace. It is spanned by all such elements. Satisfy that this. So it is easy to see that we have this, and this. So this gives a filtration and satisfy the following condition with this. Okay, given by Li, Hessian Li. Okay, then we get the graded space. Okay, this graded space is a graded vertex Poisson algebra with this, and satisfy this. So this D is also the translation operator. Okay. So this sigma p is just this map, and this y minus this is defined as this. Okay, so this filter is usually called the Lie filtration of V. This. And in the we may see that if Lie proved that FPV is actually spanned by such elements. So this is, if we take B in this and A, then we have this. So in particular, it is easy to see that F1V is this. So if we let RV just this, it is nothing else but the Zhu C2 algebra. So this is a Poisson algebra with the following operation. So, and Li also proves that this embedding extends to the surjective vertex Poisson algebra homomorphism. We have this. So also there is another filtration, usually called the standard filtration, also given by Li, Hessian Li. So now, so usually in this case, we usually assume that V is degraded, or maybe we can also assume it is CFT type. Okay. Now let AI be a set of homogeneous strong generators of V. Then we define this subspace. This is linearly spanned by such elements. So satisfy the weight. The sum of this weight is just satisfied this. So then we get this increasing filtration, and also we can find it can be checked that satisfy the following such relations. So then we have this, get a graded something this. So this graded this graded not the V, this is naturally a vertex Poisson algebra. So if we set this and this, then we have this proved by Arakawa. Yeah. So this is equal. These two subspecies is equal. And naturally, we can give isomorphism between these graded vertex Poisson algebra. Yeah. So we will use this result in our proof. Yeah. So now then we can get a graded vertex Poisson algebra for alpha VOAs. Now let G let G be a simple finite Lie algebra, and for giving K a complex number K. Now let V Kg be the associated universal alpha VOA. So then naturally we can get this filtration. So the first filtration get this. So the defined by this, right? Yeah, this sum, this. Okay. And obviously this we have this, okay, have this. The juicy to algebra is this. Okay, so now let V be a quotient of V kg by some ideal n. So then we have this RV is just the quotient of this algebra by this ideal. This ideal is just the image of n in this. So it's not hard to see that. It's easy. Yeah. Now we look at the varieties of alpha V. So first, now let V be a vertex algebra. Now, so RV is the about C2 algebra of V. Then SV is the scheme of RV. So it is called the associated variety of V. So we see that SV is a fundamental invariant of V. That sometimes it captures the important properties of the VAV. So there are some references here. So I just noticed some of them. So I'm sorry. Maybe for other things I didn't give all the references of the related thing. Yeah. Now, so here we focus on the varieties of alpha VOAs. Now let V kg be the universal alpha V associated to this k, and the finite algebra G. Now, so as we said that this Drew C2 algebra is just this algebra of a polynomial G star, and so this the variety is just this G star. We can also say that it's just G, right? So now we know that sometimes V kg is not reducible. So let L kg be the simple alpha by the quotient of this universal alpha VA. So then this C2 Drew algebra is a quotient of this polynomial algebra, and so the associated variety is just a closed G invariant conic subvariety of this G star. So this G is the adjoint group of this algebra G. So a very natural question is that what about the what can we see about this variety? Okay, because this variety, the variety of the universal alpha is easy to see, right? It's obvious, it's clear. So but for this it's not easy for some kids. So now we have the following result. So if this for the critical case, so that is the k plus the dual constant number is 0, then this variety is just the nilpotent coin of the algebra G. Okay. Now for other cases, we have the following for positive integer case. So this, because this for this case, this alpha simple alpha VOE is rational and is C2 confinite. So because given we are proved that it is C2 confinite if and only if the variety is 0 as a topological space, because so the variety is just so this RV is a Poisson algebra, is a graded Poisson algebra, the conical, so it's not hard to see that. So if it is C2 confinite, then the scheme is just 1 point. So So, and also this paper report that this is for this, it is incredible. Also, it is that this kg is C2 confined. Yeah. Okay. So for other cases, now we talk about the admissible number case. So now we call that K is called admissible if K satisfies this condition. So I think in this paper, the first, I don't know whether I'm right. So I'm not so sure. Maybe in this paper, the first. Okay, so for this, for admissible number K, so Tomoka proved that if K is admissible, then the variety is the closure of some nilpotent orbit in G. So in this case, we have this. Actually, I think in his paper, he gave, I think, through a table, he gave all the varieties, give a very clear description of all the cases. Yes. So now, but here I give some remarks. So there are cases when LKG is not admissible, but the variety is still the closure of some nilpotent orbit. So by their work, so there are also cases where this variety is neither G star nor contained in the nilpotent cone. So in general, we may see that the problem of determining the variety is wide open. So our first result is that we first we want to know that if VKG is not reducible, I mean that is the simple quotient is not trivial. So is that the variety is a proper subvariety of the G. So here we give the first proposition. So by this we can answer our question. So now suppose that because we have already know the case, the critical case. So here we assume that this is not there. Then we prove that the image of any non-zero singular vector of VKG in the Zhu-C2 algebra is non-zero. So this is the key step of our proof. So here I just give the sketch of the proof. So firstly, let W be a non-trivial singular vector of VKG. Of this universal alpha BOA. Now, we may assume that this W is in FP VKG, but not in FP plus 1 VKG. We can there is some P non-negative positive integer P. So the image of this W in this graded vertex Poisson algebra, we know that the graded the vertex Poisson algebra is just this, right? So then this is a non-trivial singular vector of this, right? Yeah. So here this is just the natural map. Okay. So then we can choose the Chevalier basis of G. We just we denote this. So L is the rank of the G, and this is the beta 1, beta q, just the consists of the system of positive roots of G. Okay. Then we may assume that this W is just a sum of such WG, where WG we just just write this way. We always can write this way, right? Okay. So this is just the E beta I. So here just F beta I, and this is just H. So first thing we have to do is that we studying this W bar in this way. Then we deduce the first result that okay, there exists I in G satisfy this just F beta I does not appear. Yeah, so just these two parts. Okay. So this is to get this, we do things in the setting of graded Poisson vertex algebra. So, but this result is not enough. So we need to prove that the image of W in the C2 draw algebra is not 0. So the second thing may be more difficulty to get the second part. So the main idea is to use the Shogawara operator. So in two ways, I think, in two ways to use this. To this Shogawara works, and I think the proof the important thing is to choose a good leading term. So this leading term is not usually as we do. We just choose a leading term which satisfies the if so here. Let me see that. So here we have this, right? So we just choose the leading term with the longest HI minus 1. That means that with the longest H1 minus CI1. Yeah, we have this, right? And I1, yeah, H2 minus C. 2, 1, yeah, G. And HL minus C L1 G. So among all the G, we choose the term which satisfies that the sum of this number is the biggest. Then we use the Shogawara operator to identify several lemmas. We here not give the details about this. So finally we prove that there exists this I in G satisfy that this WI is like this. So with this we can see that the image of W in the Drew C2 algebra is not 0. So I think with about the proof, the nice thing is that we don't have to know exactly what the singular vector is, but we just need to know there is some special terms in this singular vector. So I think, and we don't know exactly what type of G it is for general G. Okay. So with this result, so we can prove the first result of our this period. So we prove that these two varieties the same if and only if this universal alpha is simple. Okay. So now I will give some remark about this. So although we give the result, there are many questions about this. For example, we can ask whether there is a pair GK such that the variety is a maximal proper G invariant closed subcone of G. I think in general, this case is not resolved yet. I don't know the recent progress on this. So for example, if G is SL2, we know that N is the unique maximal proper G where the closed subcoin for G, because SL2 if we consider it's always, so it's clear. So in fact, the only G where the closed subcoins of SL2 is just these three. So all these subsets can be realized as a associative variety of some LK SL2. So for this case, it is done. So, but for even for GS3, I think I don't know the recent progress. I don't know, but we maybe it's solved. Because I have not talk about this in these years with other people. So now one can construct a maximal proper G where the closed subcoin of G as follows. Now we let EHF be a principal SL2 triple. So here I think I don't need to explain what's principle, right? So now let this chi be this. Is the G very close to the coin generated by this H. So this set is referred to as the principal coin in their paper. So this chi contains the nilpotent coin N, and it has dimension, this dimension, the dimension of N plus 1. So if we take G as SL3, then it is the maximum, because we can compute the dimension of SL3. Then it is easy to see that it is the maximum, because the dimension of SL3 is 8, right? This number is 6, and this is 7, so it's obvious it is the maximum. Also, more generally, for any regular semi-simple element, or we call the principal semi-simple element as in G. So this is a G where the closed subcoin of G continue in this. So now the principal somehow it is more kind of canonical, because it is precisely the closure of the set of principal semi-simple elements. So we can ask, so is there a level K such that this? I think in general it is open now. Okay. So also there are many other things. So even though we prove that if LKG is a non-trivial quotient of your VKG, so we still, for giving a G, the variety, what the variety looks like, I think in general it's not. There are many cases we don't know. Yeah. Okay, now I change to the varieties of the shooting varieties of alpha W algebra. So with our result, we can get this similar result about alpha W. So first, let me briefly introduce what is W algebra. So now let F be a nilpotent element of G, and we denote this by the centralizer of F in G. So now by the Jacques-Inverse theorem, there is this SL2 triple, right? So then we can have this presented by this relation. Then we get we can define this G equal to this. Okay, now we get the gradation of G. So we can see that this is a vector space isomorphism, and in this F can define the unique this this linear functional G satisfies this. And also it defines the not generate symmetric bilinear form of G. So in their paper, I think they assume that G is a super view, but here a super Lie algebra. So here we use the Lie algebra. So here I just assume that G is a simple Lie algebra. Okay. So if super is here is a super symmetric bilinear form in the set by this, defined by this. Okay. So then it follows that it is unidimensional, right? So now let S alpha. So this is just the index. So be a basis of this G 1/2. Then we have the Clifford addition. This is denoted by this associated with this, and with even generalists the phi in this, and satisfy this relation. Okay, now with this we can define the associated vertex structure with the field with these fields. Also, we consider this G plus this the positive part. So in the S alpha is just a basis of this part. And also S minus alpha is the basis of the minus part, okay? The negative part, and satisfy this, okay? Also, we have the Clifford finalization of this, and with all the generators, this. And the following relations with this. So also we get this associated vertex superalgebra with the field defined by this. So for example, if F is a principal or regular, so we don't have this part. We don't have this G. If F is a principal, we don't have this part. We just have this part. Okay, so now we consider the vertical part of this. Okay, and we denote F is this. Then F is also graded, by this additional defined by this. Okay, then we set this. With this Fi, we get this, right? So this gives a degradation of this CKGF, and also introduce these fields DZ. This DZ is a little bit complicated. So yeah. So this is with this and with this. And this DST, this field is defined as this. Also, this C alpha beta gamma is just the constructor coefficient of this X beta equal to this gamma. C alpha beta gamma. Yeah. So for S alpha, S beta in this part. So then with this, we can have this. And also with this. So in this way, we get a complex of vertex algebras, which is called the BIST complex of the generalized dream-field Sokolov reduction. Okay, so then we get the alpha W algebra. So with the following theorem, so if you consider the cohomology, they will give this. If I is not there, so this is there. And if it's 0, then they get the alpha W algebra. It is a vertex operator algebra. So I think when F is the principal nilpotent, so I think in this I for generic K, and the for K in the case where G equals is SL2, and they prove for the general case. Now for F general neopterin element, I think in their paper they introduced the W algebra and this, and our Tom proved that if I is not zero, it is zero for general neopterin F. So I should say that there are many results about W algebra. So many. So here I will not give the references of it because I just talk about the varieties. So I will not give all the references. I'm sorry. Yeah. So now we denote by WKGF the simple quotient of this universal alpha W algebra. So this is usually called the universal W alpha algebra. Okay. Here. Oh yes. So also, for the simple quotient of this LKG, we can also consider this, right? So this is also a vertex algebra. So it is, so if it is not zero, it is a quotient. So actually, if k is a positive integer, so it is zero. So it is, if it is not zero, then it is a quotient version of this universal alpha W algebra. So conjecturally that this, if it is not zero, these two are equal. These two are equal. I don't know whether it's completely proved, but up to 2019, it's not completely correct, but almost. So this conjecture has been verified in many cases. I think the last year the progress, I don't know, maybe I missed something. Okay, so now for this, for the universal alpha W in its variety. So it's the variety is just the slotted slash with this. Just they proved that. I think first this is for principal case. Tom Caracal proved that for the general case. Okay, and in this paper, he proved that for any quotient V of this VKG, if we take a quotient of this alpha, universal alpha VOA, then this, the variety is just intersection of this and this. So we will use this result to prove out the following result. So then the second result of our work is that let F be any neopterin element of G, then the following assertions are equivalent. So VKG is simple. If it's so, then this is equal. So 1 to 2 is obvious, right? And this, so this is equal. Just. I think we about this result. Only we need to prove the things that from 3 to 1. So with the first result we get, so it's not so difficult to prove it, because I just give the sketch of the proof. So for example, if 3 hold, then we get this, right? This is just the slotted slash. So with this result, then we have this. Also, on the other hand, so if it is not equal, then this variety is contained in a proper G inverted closed subset of G. So this slotted slash must be contained in a proper G invariant closed subset of G. But this contrasts the fact that this map this is the well known that is smoothing onto a dense open substrate of G star. So with this, then we can prove that these three statements are equivalent. So with this, we get the analogous result about the variety of alpha VOEs. Okay, so that's to the end of my talk. Thank you very much. I maybe just 40 minutes. So I'm sorry.
Oh, that's great. No, don't worry.
Yeah.
This is